All right, lesson 3-9. 3-9 is, in some regards, a fun lesson because we finally learned today. We've been dealing 9 lessons of trig, and we actually haven't learned how you practically solve anything in the real world with it. I've been laying a foundation. Today is the first day that algebraically you learn how to solve with it. So let me frame it up this way. This year, we've dealt with stuff starting in Unit 2 where we had what I call PEMDAS. You're used to PEMDAS, but I throw in the L. Do you remember what the L stands for? Logarithms, yeah. And so the way that we solve things is we do opposites. For example, let's say an equation you were solving for x and it said x plus 5. And I said, hey, how do you solve for x? What's the opposite of adding 5? You would say the opposite of adding 5 is subtracting. Okay, y'all know that opposite. Well, then we have, as you further your math skills, we get to multiplying and dividing. So if it said 5 times x, how would you solve for x? You would divide. Okay, and then we go further. What if it was an exponential? What if it was 5 to the power of x? No, not square root. That's if it's x squared. What if it's 5 to the power of x? What's the opposite of exponentiating? Logging. We learned that. Today, we're learning what's the opposite of a sine. And the answer is going to be a sine inverse. What's the opposite of a cosine? A cosine inverse. And what's the opposite of a tangent? Tangent inverse. I'm going to teach you about inverse functions today. And we're going to take 2 different approaches. I'm going to show you analytically. That just means the pure algebra. And I'm also going to show you graphically. And this is where I'm going to show you a unit circle with an intersection. So I'm going to use a unit circle to help you graphically understand what's happening. And analytically, which means just pure algebra. You need to know by the end of this course how to do one of them really well. You don't have to be able to master both. You need to be able to master at least one technique. If you can master one technique, you're great. I'm going to show you both today, but that's what we're looking at, the inverse functions. There's a key in here as well. They're all going to have a restricted domain, which we'll get to when I get to the pictures. They're going to have a restricted domain. It's the only way it works. So that's what we're looking at today, 3-9 inverse trigonometric functions. So now let's dive into the inverse sine function. So up here, it walks you through something you can read later. I want you to recall when we did inverses, to find an inverse, what actually happens to the equation? You switch the x and y. And so what this is going to walk you through is some tests that we did. So let's just say we start with the sine function. What an inverse function will do is it will switch the x and y variable. So it'll take your equation and it'll switch those variables like that. So this would be the inverse here. Now, if you recall from lesson 2-8, that whenever you find an inverse, what you do is you switch your x and y, then you would solve for the new y. And so the algebra, just to give you a teaser for where we're going, the question is going to become is what, if you're solving for this y, what's happening to this y? Well, it's being signed, if you will. It's being signed. What's the opposite of a sine function? You're going to say the opposite would be a inverse sine. And so what happens is the way to look is we'll say, well, it's the inverse sine of x will equal, and on this side it would be the inverse sine of sine y. What will we do with the inverse sine and sine? Since they're opposite, they will cancel, and that would produce that y equals the sine inverse of x. That this is the inverse of that. These are inverses of one another. Inverse means they undo one another. What one function accomplishes, the other cancels out. So for that to happen, what you would do graphically, if you remember, to check if something is a function, what we always did in Algebra 1 and Algebra 2 is we check to see if a function passes the vertical line test. So here's the sine wave. Everybody seeing where I'm looking on this bottom left-hand corner? That is the sine wave. Question for you, does the sine wave itself pass the vertical line test? Which means sine is a function. Well, what we learned on lesson 2-8 is to determine if something has an inverse function, you would actually try the horizontal line test. Now, would the sine wave pass the horizontal line test? No, which means sine itself, without restricting the graph, restriction, if you remember, means we cut off part of the graph. Without cutting off part of the graph, it would not have an inverse function because it fails the horizontal line test. The way we describe that is we'd say, For sine, it does not have an inverse function because not every member of the output has one and only one input. That's how we wrote it on lesson in unit 2. Now, so what are we going to do? We're going to cut off part of the graph. So notice what they've done here. They've taken the minimum that's closest to the origin. That's the closest minimum to the origin. They take the maximum that's closest to the origin, the first minimum and the first maximum. You see how that's the first minimum and first maximum? They're going to say, we're going to look at only the graph from the first minimum to the first maximum. That's going to be the only portion of the graph we look at. Everything else is going to get cut off. So if you go from graph 1 to graph 2, what's the difference on graph 2?
Not periodic.
I hear it's not periodic. That's true. But what's ultimately I want you to see visually that happened? We cut off part of the graph. What do we cut off? We cut off the values starting here, going to the right. This is at pi over 2. How do I know that's pi over 2? Because this mark says pi and this is halfway. And if this is negative pi, then what's this mark? Negative pi over 2. They cut off any graph outside of the interval negative pi over 2 to pi over 2. Make sense? That's all that's left. Now, when you take an inverse, you told me a minute ago, what do we switch? The x's and y's. Okay, so look here. What is this x value? Negative pi over 2. What's this x value? Pi over 2. When you look over here, what is the y minimum? Negative pi over 2. What's the y maximum? So the x minimum and maximum became the y minimum and maximum. And now look at the y-axis. What's the y minimum? Negative 1. What's the y maximum? When you look at the inverse, what's the x minimum? Negative 1. And the x maximum? Positive 1. You see what happened there? So the graph, notice this was a portion of the wave right here. A portion of the wave, it got restricted on the outside. That means cut off. And then we switch the x and y's, which make it it curves differently now. So it's a slightly different curve. They still appear a little wavy, but technically if you did not restrict it, it would be waving on the y-axis as opposed to waving on the x-axis. So that's what happens. Okay? Now that's a long introduction. Let's look at our table. What's going to happen, and I'm going to jump into the unit circle here, is the part of the graph that gets cut off when you look at the sine function. Remember, sine is y. The part of the graph that's going to get cut off, actually, let me put sine x here because I use an x. The part of the graph, actually I have a theta in there. I'm going to leave it as a theta. Okay, sorry. The part of the graph that's going to get cut off or restricted is the left half. I'll say it this way because this is how it's going to be true for cosine as well. Sine is y. What you restrict then are not the y values. We have to have all the y values. You can't cut off the y values. What you restrict are the repeating y values, which happen when you have a negative x. So I want to say this. When we restrict the graph for inverse sine, we're going to restrict the negative x's. I don't restrict the y's. That's why I'm not touching the y's. I'm touching the x's. I'm going to restrict the negative x's. That's how it's going to work. So our graph is going to exist anywhere from what looks like the fourth quadrant to the first quadrant. But let me go back here. The part of the wave that we take is we don't take the fourth quadrant values from 3 pi over 2 to 2 pi. What we take is the fourth quadrant that would be on the negative side, which means this. What I want you to label in, the output values are actually going to be the pi's going from negative pi over 2 to positive pi over 2. That's what are going to become our answers with 0 in the middle. So 0, pi over 2, you should know those two values. We're going to call the fourth, this quadrant right down here, the line between the fourth and the third. We're going to call that negative pi over 2 rather than positive 3 pi over 2. Okay, right now you're probably confused. Forget about being confused. Let's use our hand trick real quick to find these values. If I were going to find sine of negative pi over 2, that's going to be this y value right here. That's negative pi over 2. If I want to know the sign there, will it be a positive number or a negative number when you're down low since y is sine? Negative. We should have a negative answer here. Which finger do you bend for negative pi over 2? Bend your thumb. Bend your thumb, flip your hand over. How many y's do you have at that spot? 4. So the value is going to be negative square root 4 divided by 2. Sine and cosine, remember, they're always divided by 2. We have 4 y fingers. Now I'm going to find negative pi over 3. Negative pi over 3 would be located somewhere in here on the unit circle. So one more time, would y be positive or negative if you're down low?
Negative.
Negative. Okay, which finger is your pi over 3 finger? Pointer. Then your pointer, flip your hand. What are you getting there? 3. So it'll be negative square root 3 divided by 2. At this stage, I want to remind you sine and cosine and tangent, they follow a pattern. So I'll do one more and you'll probably know what the pattern is. Let's move the red dot a little bit more. This is negative pi over 4. Negative pi over 4. Will it have a positive y or negative y? Negative y value. Okay, which is our pi over 4 finger? Middle, bend your middle, flip your hand. What are you getting for y's? 2. So it's negative square root 2 over 2, because sine and cosine are always divided by 2. You probably see the pattern now. What's going to be negative pi over 6? Very good. It'll be negative 1 over 2 when we reduce. I'm going to do unreduced first. So I'm going to do negative square root 1 over 2 first. Okay? What about when we get to 0? 0 is this spot right there. Is y now positive or negative?
Neutral.
Neutral. Good. Trick question. It's not positive or negative. The pinky would be your finger. If you bend your pinky and flipped your hand, how many y's do you have there? 0. So that's why we're square root 0 over 2. It's neutral. Now I get to positive pi over 6. That's up here. Pi over 6 is somewhere in there. Will this be a positive y or negative y? Positive. Pi over 6, which finger was that? Ring. Bend your ring, flip your hand. How many y values do you have there? 1. So it's square root 1 over 2. Now we surely see the pattern. What's happening to my numerator each time? The square root is increasing by 1. So this will be square root 2 over 2. Can I just fill it in by pattern now? Square root 3 over 2. And finally, the last one would be the square root of 4 over 2, which is the maximum sine value. That's when this dot is as high as it'll ever be. Now, I'm going to reduce these. I know a lot of times I just leave them as is. I'm going to reduce the ones I can. What is the square root of 4?
2.
That becomes a 2. So it's negative 2 divided by 2, which becomes negative 1. Good job, Daisy. I heard you jump all the way to the answer. I'm going to go over this end. Positive square root of 4 over 2 is going to become positive 1. Okay? Then one that I think is next easiest is square root 0 over 2. What is the square root of 0? 0. Divide that by 2. 0. Okay? The ones I think are next easy are the square root of 1s over 2, the positive and the negative. What is the square root of 1? 1. So this will be negative 1/2. This will be positive 1/2. The last 4 do not reduce. Those values are as reduced as they ever can be. Whoops, that's not what I wanted to do. I was hoping just to, that won't let me do it. Well, I'll leave those as is. Okay, so there's our chart. Now, why do we have that? That's a cheat sheet for the next slide, but I'm going to actually do it different. For the next slide, it's going to ask us to find inverse. Now, what do we do for an inverse? Do you remember? Switch the x and y. This is input. This is output. So let me go ahead and write that in there just to make sure everybody's clear. For what we just did, this was the input. This is the output. So when you deal with the inverse, what's going to happen with the input and output? Switch. So this is going to become the input values you'll see in the next slide. These will be the type answers that we get. Everybody tracking with me? Okay. So now, let's actually start to practice this. So if you can call it example 1 if you like, let's practice this. You can use the previous table to get all the answers, but I'm going to use the hand trick and some algebra in the process as well as graphically. I'm going to show you multiple ways of doing this. So first, I'm going to act as if we don't have the previous chart. Now, what do I mean? What you could do is this. If it's sine inverse of 1, what you could do is you could look at this table, and would you look, if it's sine inverse, would you look here for my input of 1? Or would I look in the output column for 1?
Yep.
Yeah, because this says inverse. That means these switch. And so you'd look for the value 1 here. Where do we see a 1? Right there. So the answer is going to be pi over 2. Now let me show you why it's pi over 2. Okay, so here's how you do this to find out the answer is pi over 2 without that table. When you're working with sine inverse, this means you're going to be working not with the palm of your hand, you're working with the Back of your hand. For sine and cosine, you always needed to be divided by 2. So what I'm going to do here is I'm going to rewrite this as sine inverse, and I'm going to multiply by a funny looking 1 so that I'm dividing by 2. Everybody okay with that? I've multiplied my number by a funny looking 1, 2 divided by 2. What this will do is get me the correct denominator. Everybody tracking? So that is the same thing as sine inverse of, what's 1 times 2? Just 2 over 2. Last, what I will do to get my value is I'm going to convert the numerator to a square root. So to know what the square root is that produces a 2, you do the opposite on the inside. What's the opposite of a square root? Square. So what I'm going to do is I'm going to rewrite this as a square root, but I'm going to put the squared number. What is 2 squared? 4. That means what I'm looking for on the hand trick is the square root of 4 divided by 2. I don't know if that tracks with you, but sine inverse of 1 is going to be equivalent to sine inverse of square root of 4 over 2. So go to the back of your hand. We need 4 Y fingers. So from the top, count 4 Y fingers. Go pinky, ring, middle, pointer. That's 4, right? Bend your next finger so you have 4 remaining. 4 Ys remaining. Now flip your hand over. To evaluate a sine inverse, you flip your hand to the palm side. What does your thumb represent? Pi over 2. Thus, the answer is, like the table said, pi over 2. The answer is pi over 2. Does that make sense on how to do that? If you hear me say the analytical way of solving, that's what this is right here. This is the analytical. On the notes, it said we are going to look at it analytically and graphically. That's the analytical, is writing equivalent statements and using your hand trick. Now, let me show you the graphical representation. The graphic, if you want to do these today, what you're going to be drawing each time as quickly as you can is we will draw a unit circle with an X and Y axis. Just like that. I want you to recall that on a unit circle, the reason we call it a unit circle is that the radius is 1 all the way around. Meaning this, that this point right here, let me put X here. I'm going to put Y equals sine. That this point right there would be right 1 unit, and so it would have a coordinate of 0, 1, whereas this point would be up 1 unit, so it would be 0, 1. 1, 0, 0, 1. This point would be -1, 0, etc. So what am I trying to tell you? The radius is how long on a unit circle? 1. When you're doing a sine inverse, what that's telling you is your Y value. The Y value is 1. So graphically, what that would look like, Y equals 1, if you put that in your calculator, it would be a horizontal line, and it would go through at a height of 1. So this graph right here, if you go up 1 unit and you drew a line, that's the value Y equals 1. What an inverse will do is an inverse will find the amount of radians at the intersection of the line, the Y value, the sine inverse value, and the unit circle. What amount of pi's is required to get me to that intersection? How many pi's do you need to get you there? Pi over 2. That's why the answer is pi over 2 visually. So that's your graphical representation. Now, Felix, stay with me here. The one thing I need to add to this graphical representation is when you do an inverse, we will never, ever, ever take an answer from the left side of the graph. This is the part that gets restricted on an inverse. So what I want you, if you're following along here, I want you to draw a line to the left side and put restricted. That does not matter on this problem. It will matter on other problems. So that is our restriction right there. All of this gets restricted. That will matter in the future, just not on this problem. But that's the process. So I know that that's a lot of information. Rather than spending much more time doing this one, I'm going to move on to the first, and I'm going to do it 4 times. So if you don't catch on this first time, it's okay. If you don't catch on the second time, it's okay. Hopefully, by the 3rd or 4th, you'll catch on to how this works. Make sense? Okay, here's the analytical approach. Analytically, sine inverse of negative 1/2. What you do is first ensure that the denominator is a 2 if you're using your hand trick. Not using, what we could do is cheat and look on the table. Where do I have a negative 1/2 on this table? Not negative pi over 4, negative pi over 6. That's going to be our answer. We could just cheat and look at the table there. Okay, but without cheating, what you do is you ensure that the denominator is a 2. Is my 2, do I have a 2 for the denominator right now? Yes, I do. So then you go to the numerator and you make sure it's a square root, which this one's not. So what do? I square 1. If I square 1, that's what number goes inside the square root. What is 1 squared? 1. Okay, you write it this way. Now from there, I can use my hand trick. So sine inverse, when you're doing an inverse, you don't use your pi side of your hand. That's the palm. You use the back side of your hand. So look at the back of your hand. We need one Y finger. So Y's, are they on the top or the bottom? Top. Count one finger, which would be your pinky. You bend the next. You're bending your ring finger, which leaves you with one Y. Everybody follow? Flip your hand over to evaluate the inverse. Now you're on the pi side. What does the ring finger represent on the pi side? Pi over 6. Now, do you remember, was our answer supposed to be pi over 6? What was our answer supposed to be? Look at the table again. Negative pi over 6. Here, with sine and cosine. Excuse me, I misspoke. For sine and tangent, they're inverses. If you have a negative input, you will have a negative output. I'll say that again. For sine and tangent, if you have a negative input, you will have a negative output. Conversely, if you have a positive input, you will have a positive output. Yep. For sine and tangent, if you have a negative input, I'm talking about the inverse right now. If you have a negative input, your output will also be negative. Remember, we're switching the input-output for the inverse. Notice, if you have a positive input, what kind of output will you have? Positive. Okay. Now, let me show you why this is true graphically. Once again, quickly draw a unit circle. It doesn't have to be a very big unit circle. Put your x-axis and y-axis on there. Y represents sine, so I'm going to say y equals sine theta there. There's my x-axis. Now, what always, no, I'm not going to tell you the restriction yet. Okay, we want negative 1/2. This is a y value because sine is y. Go to your graph, wherever you think, remember this is down, this point right here is 1 unit down. If that point is 1 unit down, negative 1/2 is halfway there. I'm going to say it's about right there. Are you following me? That's about halfway down. So that's roughly negative 1/2. Now, why does that matter? What you should do is to have a horizontal line like I did here, but this time we're going to have y equals negative 1/2. That's what the line I'm about to add. Come to your unit circle, do y equals negative 1/2. Just like that. Now the solutions would be any intersection between the circle and the line. How many solutions do I have right now between the circle and the line? How many intersections between this circle and this horizontal line? 2. One here and one there. When you deal with inverses, though, you always restrict a half of the graph. Since sine deals with the y's, you don't restrict any of the y values. What you restrict are the negative x's. So restrict this side of the graph. So now I have a question for you again. How many intersections do you now see between the circle or semicircle and the line? We now only have one solution. The solution is going to be this one. If I draw a line through there like that, would this angle be coming from 0? Is this angle a positive angle or a negative angle? Negative. That's why it's negative pi over 6. is because the angle is down. That is negative pi divided by 6. That's why we have a negative answer this time. Now again, you might not catch on yet, but hopefully within the next two, you catch on to how this works. Okay? Part C. If we wanted to cheat, we could look at the table. We're looking for sine inverse of square root of 2 over 2. You would look at sine's table, but you would look at the output for square root of 2 over 2. Where do you see the square root of 2 over 2? Here? What's the answer going to be? Pi over 4. The answer should be pi over 4. All right. So what do we just say the answer is? I've already forgotten. It's going to be pi over 4. Now let me show you why. This is actually, well, this time it's actually already in good form. It has 2 for the denominator. It has a square in the numerator. So go to the back of your hand. So flip your hand back over. Count 2 y's. The first y is your pinky. The second y is your ring finger. We're bending the middle finger. Flip your middle finger over. What does your middle finger represent in terms of pi? Pi over 4. Again, the way sine and tangent will work is if the input is positive, the output will also be positive. If the input is positive, the output will also be positive for sine and tangent. If the input's negative, the output will also be negative. Graphically, here's the reason why. Quickly, unit circle. We're dealing with the y-axis, so I'm not just going to put y up there. I'm going to put y equals sine theta. But I'll only put x over here because I'm not dealing with cosine, so I'm just going to do y equals sine theta. This is a unit circle, which means the circle has a radius of 1. Square root of 2 over 2. I'm not sure exactly what that is as a decimal, but it's something less than 1, and it's going to intersect the circle halfway up. So make sure your circle, you're like halfway through the circle, something like that. That would be the y value, square root 2 over 2. I'm not sure what that is as a decimal, but that's it. At this stage, how many solutions do you see? 2. Will we have 2? No. So we need to restrict this. Once again, when you deal with sine function, you need all the y's. So you can't cut off any of the y values, but you can cut off the negative x's. That's what I can cut off. So let's cut off these negative x values. That I don't need, so we're going to restrict that part of the graph. If this part's restricted, now I only have one solution. I have whatever this solution is going right through there. And we said what amount of pi's would be necessary to get a y value of square root 2 over 2? We said that would be pi over 4. That's correct. That would be pi over 4. The input has now become the output whenever you take an inverse. Usually the pi's are the input. Now they're the output. That's our answer. That's why it's pi over 4. All right, last one, part D. This right here. Let's walk through the process. This is not in good form for us to use hand trick on right now. So what's the first step? Multiply by a funny looking 1 to have a denominator of 2. So it'll be negative 3 times 2, which is negative 6. All right, so now I've got a denominator 2. Perfect. Now we need to get the numerator as a square root. So to get it as a square root, we have to do the opposite, which is squared. What is 6 squared? 36. Perfect. So we're going to rewrite this as sine inverse of the negative square root 36, again, because that would produce a 6, divided by 2. All right, so here we go. Hand trick. If it's sine inverse, you're looking at the back of your hand. I want you to count 36 fingers from y, and then we'll bend. Okay, now I'm getting some chuckles. I'm like, wait, what? Well, this says to get 36 fingers. Do we have 36 fingers? No. This is one of those values that's going to be undefined. This right here, all of these values are undefined. You can't do it. This is undefined. Now, if you're not sure why is it undefined, well, I'll tell you why. Graphically, it'll make a lot more sense. Graphically, what I'm going to do here, once again, is I'm going to draw a unit circle. This time I'm going to draw a really small unit circle. What makes something a unit circle? What makes it specifically not just a random circle, but a unit circle?
If the radius is 1.
It has a radius of 1. Now this time I'm going to draw a longer y-axis down like that. So I'm looking at sine. So y is equal to sine theta. Here's my x-axis. A reminder, that point there would have the coordinates 0, -1 because the radius is 1. Okay, perfect. We're saying the y value is -3. If this is a y value of 0, if that's a y value of -1, the -2 would be somewhere in here. Would y'all agree with that? And -3 is somewhere down there. What I would have is a horizontal line representing y equals -1 that goes through there. That is the y value of negative, I think I said -1. I meant to say -3. That's the y value of -3. How many times does this line intersect the circle? 0. We don't have an answer. And you would still restrict the side. All that's the same. This part would be restricted. But it does not intersect. Since there's no intersection, you have no solution. No real solution. I'll write that in. No real solution. Since y equals 3, -3, sorry, does not intersect the unit circle. Now, how do we know that analytically? We did not have 36 fingers. That's how we knew it was going to be undefined there. We didn't have 36 fingers to work with. How do you know graphically? Because the line equals y equals -3 line does not intersect the circle. Okay, that's your foundation for inverse sine. So with that, we're going to go back to the packet and try DOL number 1. Our first DOL today, well, let's try DOL number 1. Let's take a look at the inverse cosine now. Now, once again, here's cosine. Cosine has what shape? A wave. If I were to ask you, is cosine a function? You would test with a vertical line test. Does it pass the vertical line test? Yes. Now, if I ask you, does cosine have an inverse? That's a function, sorry. Does cosine itself have an inverse that's a function? What's the correct answer? No, why not? Fails the horizontal line test. By definition, on lesson 2.8, the way we said it is, cosine would not have an inverse function since every member of the output does not have one and only one member of the input. That's how we said it on lesson 2.8. So what do? Just like on sine, we restrict the graph. You go from the first maximum to the first minimum, which brings us to a problem here, is that honestly, you have another minimum that's just right here that's just as close. But what mathematicians have decided to do is to take the maximum and minimum that's positive as opposed to the maximum and minimum that's on the negative side. They just decided to take these values. Does that make sense? So there's the part of the graph we're going to include. So what do you do with the part of the graph you don't include? It restricts. It's going to get cut off. And now you have a little bit better idea of what I mean by that because we did all those unit circles. That part gets cut off. So now look at this graph compared to the second graph. It's still cosine, but this is cosine with a restriction. This restriction, how far left does this graph go? 0. So it goes from 0 less than or equal to x, which is less than or equal to. Now how far right does it go? Pi. Notice that's going to be the top half of the circle. So this part of the graph that we keep is from 0 to pi. Okay, now the inverse, what happens when you do an inverse? You switch x and y. So these x's of 0 to pi become the y-axis from 0 to pi. And the y values become the x's. This is a maximum of 1, a minimum of -1, check over here, a minimum of -1, and a maximum of 1. That's what cosine inverse is going to look like. Still a wave, but now it's a wave on the y-axis as opposed to a wave that follows the x-axis. That's what happens. Okay? Questions over that? What's different on it cosine is you will not have, you can have negative inputs, but you will not have any negative outputs ever. Your outputs will be anything from 0 to pi. Okay, so showing you this on the circle. With cosine. Cosine is which variable again? X. Come over here, put x equals cosine theta. You have to keep all your x values. So I don't restrict the left side of the graph because I need all x values. I need the positive x values. I need the negative x values. What values do you not need for cosine though?
Negative.
You don't need your y's. So what we do is we keep the positive y's. We eliminate the negative y's. That's how my restriction is going to be for cosine. Cosine's restriction is different. Than sines, and it'll be sines is going to be the same as tangent. So cosine's restriction is going to be different than sine and tangent. I'll put it that way. Sine and tangent will restrict the left side of the graph. Cosine, we restrict the bottom because we need all x's, but we don't need negative y's, if that makes sense. Okay, so let's go up here, fill out our table. This is cosine. Let's just think about it as a unit circle. We'll probably go faster. What is this value on cosine? What is the maximum value that x could ever be? 1. That's a maximum of 1. Our first cosine value will be 1. If you want to write in, this would be the square root of 4 over 2. If you want to put the hand trick value, it would be square root of 4 over 2. Pi over 6, that's when you move to about here. We're still a positive x value. It'll still be positive. Pi over 6 is your ring finger. You bend it, flip it. Now how many x's do you have? Square root 3 over 2. Okay, tell me the pattern. What's going to happen here? They're decreasing. So that'll be square root of 3 over 2. Then we will have square root 2 over 2. The next one will be the square root 1 over 2. What will that reduce to become? 1/2. Good. Then we would have the square root of 0 over 2. If you want to put that dot on there, that would be right there. That's where we're located right now. That is pi over 2. If this was 0, this is pi. This is pi over 2. That's not a good color. You can't see that very well. Let me change this to black. If we start at 0, we're now halfway around this semicircle. And so square root of 0 over 2 will reduce to become 0. That's an x value of 0. Right? That right there is the coordinate 0, 1. Continuing on. Now, notice I'm getting to negative x's, but these are not negative pi's. If you're in the second quadrant, that means you're almost 1 whole pi. If your denominator is 3, what number is almost 3? 2. But this is going to produce a negative x. So 2 pi over 3 will produce the negative square root 1 over 2, which is negative 1/2. 3 pi over 4, that means it's almost 1 whole pi. That pi over 4 will produce negative square root 2 over 2. 5 pi over 6, notice once again, it's almost 1 whole pi. It's a negative, it produces a negative x though. Therefore, the answer would be negative square root 3 over 2. And finally, if we went all the way around to pi, what's the minimum value on a unit circle? It would be negative 1. And the coordinate would be negative 1, 0. That's the minimum. Therefore, this value will become negative 1 because it's the negative square root of 4 divided by 2. Okay, so there's the values you could see. Now, if we wanted to go fast on the practice part, if we wanted to do this really fast, it says cosine inverse 0. Where would you look at? Would you look at the original input, or would you look at the outputs for it, trying to find the inverse? Which column would you look at if you for 0 if you're trying to find the cosine inverse? Do you look at the input or the outputs? Outputs. You look on the outputs for 0, and what would our answer then be? This should be pi over 2. For cosine of 2, do we have a 2 on here? This is going to be undefined. Cosine cannot get out to 2. That would be undefined. How about 1/2? What's cosine inverse of 1/2? I'm oh, there it is. Pi over 3. Perfect. And finally, what about negative square cosine inverse of negative square root 3 over 2? What's that answer going to be? 5 pi over 6. Now let me prove it to you. Okay, you all see how you could cheat your way through there using the table? Okay, let me cheat your way through. If you're doing an inverse and you're doing analytical, that means like hand trick stuff. The first thing you have to do is have it divide by 2. So you need to multiply by a funny looking 1. That's the first step. We make it divide by 2. Secondly, well, I'll reduce that. What is 0 times 2? 0. Okay, then you turn that into a square root in the numerator. What is 0 squared? So it'll be the square root of 0 over 2. Now you can do your hand trick. So you go to the back of your hand. You need 0 x's. Which finger do you bend to have 0 x's? The thumb. Flip your hand over. The thumb on the pi side is pi over 2. That's why the answer is pi over 2. I know we already had it from the chart a second ago, but that's why cosine inverse of 0 is pi over 2. To show you this visually, I'm going to try to go a little bit quicker here since we've already solved it. On a unit circle, cosine deals with which variables? Next, so this time I'm going to write x equals cosine. And I'm only going to put a y on the y-axis. I'm not going to write in sine because I'm not dealing with sine. We're looking for a cosine, which is an x value of 0. This would be a vertical line. To have an x value of 0 would go through like right there. That's the line x equals 0 right there. Now we need to restrict. Cosine, you need to have all x's. What do you not need to have, though? All the y's. So do we eliminate the positive y's or the negative y's? You eliminate the negative y's, which means now I only have one potential answer. Now the only answer is this value right there. What is that in terms of pi? How many pi's does it take to get to this point right there? Pi over 2. That's why the answer is pi over 2. Okay, let's try the next one. We said this one's going to be undefined. Let me show you why it's undefined. The first thing you would do is get a denominator of 2. So I multiply by a funny looking 1. Felix, what's 2 times 2? 4. So we have cosine inverse of 4 over 2. Now that I have 2 in the denominator, I need to make the numerator be a square root. So what is 4 squared?
Oh,
Not 2. What is 4 squared? 16. So we have the square root of 16 divided by 2. This means you go to the back of your hand and you count off 16 x fingers and then you bend. What's the problem there? We don't have 16 fingers. So this would be undefined. That's why this all here is undefined. Okay, let's see if you're catching on. Graphically speaking, I'm about to show you why it's undefined. Why will it be undefined without me telling you? Could you tell me why this would be undefined? Deo says yes. Why do you think it's going to be undefined when we look at the picture?
it's not going to be hitting. It's not going to be intersecting the unit circle.
Perfect. It's not going to be able to intersect. So I'm going to draw a longer x-axis this time because I'm going to need a little bit extra space. But x is still cosine. I'm just going to put y. I'm not dealing with sine, so I'm just going to put y. We will still restrict the same side of the graph. X is cosine. You need all x's. You don't need the negative y's, though, so we restrict that part. All inverse functions have a restriction. Actually, I've been writing restricted. So all inverses have a restriction. That's it right there. Okay, now we need the cosine to be the x value of 2. On a unit circle, the farthest it goes out is 1. X equals 2 would be way out here. That's 1. 2 is somewhere out here. Does that make sense? Does that line at x equals 2, does that line intersect the circle? No. No intersection, no solution. No intersection, no solution. There we go. No intersection, no solution. No intersection leads to no solution. That's why. Okay? You feel like you're catching on a little bit? Let me ask you right now, is this informed to use a hand trick? Dividing by 2. Do I have a square in the numerator yet, though? No. So how do I make it a square root? You do the opposite. What's the opposite of a square root? Squared. Let's square 1. What is 1 squared? 1. So put the square root of 1 over 2. Now we can do the inverse. For the inverse, which side of the hand do you look at? The palm side or the back side? The back. You need to count one X finger. It's their thumb. You bend the next one. I'm banging my pointer finger. Flip over your pointer finger. What is your pointer finger represented by? Not pi over 2, but pi over 3. It's a pi over 3 answer. Now, cosine's not quite as easy as sine and tangent will be. Sine and tangent, if the input's positive, the output's positive. If the input's negative, the output's negative. Cosine, you have to pay attention on if it's first quadrant or second quadrant. So cosine is which axis again? The x. So when I draw my x-axis, this time your x-axis doesn't have to be as long because we know we have a good answer. So x equals cosine is there. There's my y. The cosine, we need to have an x value of 1/2. That's halfway. If this point is 1, 0, then 1/2 is halfway there. It's like right there. That's 1/2. Draw a line, if you're doing the unit circle with me. Right there. That's when you have an x value of 1/2. Right now it looks like 2 solutions. It looks like 2 solutions. Will we have 2 solutions for an inverse? No. Why will we not have 2 solutions for an inverse? Because you have to restrict the graph. So cosine's x, you need all x's, but what do you not need? The negative y's. You do not need the negative y's. So that part gets restricted out. If that gets restricted out, now how many solutions are left? 1. This solution. Would this be 1 pi over 3 or a different amount of pi over 3's if you're first quadrant?
1 pi over 3.
That's 1 pi over 3. Our solution here is 1 pi over 3. That right there is pi over 3. So cosine's a little bit trickier because you have to figure out how many pi's it actually is. It'll always be a positive amount of pi's. It's just a matter of, is it 1 pi over 3 or would it be 2 pi over 3 and etc. Last one. Cosine inverse negative square root 3 over 2. Is this in good form for a hand trick? Yes, it is. We got a denominator 2. We have a square root. Perfect. Go to the back of your hand. You need 3 x's. Count from the bottom. Thumb, finger, middle. Bend your ring finger. To evaluate a cosine inverse, you flip your hand over. We're now palm side. What is that as a pi? Pi over 6. So what we know is that the answer has to be a pi over 6. Here's the deal. If it's negative, it will not remain as just pi over 6. It will change. If it's a negative here, the pi over 6 will change. It will not remain as only pi over 6. Let's figure out what it'll become. Draw a unit circle. X-axis, y-axis. Since we do know we have an answer, I don't need to extend my axis. I can just leave it like this. Which variable is cosine again? So x is equal to the cosine of theta. Y goes there. I have a negative number. I don't know what that is as a decimal. I think it's like negative 0.8, give or take. I think. Negative 0.8, negative 0.9, something in there. So go over left. How far left is this point right there? That would be negative
One.
1 comma 0. So negative 0.8, it's going to be really close. It's something like that. Okay, it's really close. I don't remember what it is exactly, but I'm just going to say that's x equals negative square root 3 over 2. At this stage, how many solutions does it look like it has? 2. Will it actually have 2? No. So we restrict which part? If you're doing cosine, what can you restrict? The negative y's. These get restricted. So we have one solution. It's this pi over 6 out there. That pi over 6 is not 1 pi over 6. That pi over 6 is almost 1 whole pi. What number is almost 6? 5. This is 5 pi over 6. The correct answer this time is 5 pi over 6 because that is almost 1 whole pi. That's how the second quadrant works, if you remember that. So the answer here is 5 pi over 6. All right. Spent a lot of time practicing cosine. Let's go try number 2 on the back of your DOL. DOL number 2. All right, now we're going to look at the inverse of tangent, and then we're going to apply this stuff. So everything starting the same way. If I ask you about tangent itself, is tangent a function? Does it pass the vertical line test? Yes, it passes the vertical line test. Does a tangent have an inverse that's a function? No. Why does it not? It fails the vertical or the horizontal line test. So what do we do to get around that? We restrict it. We look for the closest minimum and the closest maximum to the origin. Here's the origin. I look for the closest minimum, which this doesn't actually have a minimum, but it has this arrow, and the closest maximum. You follow? This is going to be the part of the graph we use. Which means anything to the left we restrict, anything to the right we restrict. You follow along with that? So this part gets restricted. This part gets restricted. Everybody cool? So when I look at this graph here in the middle, that's showing you this section from here to here. Everybody still okay? I'm going to label this because it doesn't show the x-axis label. This value is half the right asymptote is half the way to pi. What is half the way to pi? Pi over 2. Put pi over 2 on this axis. That is pi over 2. This left asymptote is half the way to negative pi. What would this asymptote be? Negative pi over 2. Add that to your graph. Notice again, it does not have a maximum or a minimum. The only thing left to do now is to apply the inverse. What does it mean to apply an inverse? Switch x and y. So this negative pi over 2, which was the farthest left, now becomes the lowest point. Negative pi over 2. You see how that's negative pi over 2 right there? And then the farthest right, the pi over 2, now becomes the highest the function ever becomes, positive pi over 2. You cool with that? Instead of making an S curve, that's always increasing, going, well, an S curve following the y-axis. Now it's like a S curve following the x-axis. Everybody see that? That's the inverse tangent. Okay, with that, we're going to get started. The inverse tangent, to pick up, I think y'all are probably catching on quick. Why do you think half this circle is white and half this circle is gray? This is restricted. Tangent is like sine. Tangent involves an x and a y. It involves x and y. So what they do is they restrict the negative x's. You can actually get all the values of tangent. If you remember, their tangent's period was just 1 pi. You can get all of its values right there. You don't have to have negative x's to get all the inverse tangents. You can do it just right there. So tangent is going to begin with an asymptote at negative pi over 2. And it's going to continue and finish with an asymptote at positive pi over 2. That's why it's a dashed line there on the inside. That's why I dashed it. So all the values are going to exist in there. Tangent's values, they're going to start at negative pi over 2. Is that going to be a negative tangent? Tangent slope, remember. Will this be a negative or a positive value when we begin? Negative, and it'll increase all the way around. Make sense? Okay. First value, for the sake of time, I'm just going to hit these. It's going to be undefined. No, I'll write it in. The first value would have a negative square root 4 over the square root of 0. The next value, if you moved along the unit circle, would be the negative square root of 3 over the square root of 1. The next would be the negative square root of 2 over the square root of 2. Then we'd have a negative square root 1 over square root 3. It looks like you're losing a y finger every time and the x finger is gaining. We come to 0 and you've run out of y fingers. So now what happens? That means we've gone half the way. Now what starts happening on the hand trick is now we start losing x fingers and they start becoming y fingers. So this is going to be square root 1 over square root 3, then square root 2 over square root 2, followed by the square root of 3 over the square root of 1, and ending with, okay, the most important thing that you need to know on this, are you allowed to divide by 0? These two values will be undefined. That's the most important thing you know, is that the inverse tangent and tangent itself has asymptotes. Now, if I wanted to go through and reduce, square root of 0 over square root of 4 is just 0. That's the easiest one in there to reduce. Square root 1's over, or excuse me, the negative square root 3 over square root 1. What is the square root of 1? Those just become the negative square root of 3 and the positive square root of 3. What happens when you have the square root of 2 divided by square root of 2? You get 1. So this is a negative 1. This one is a positive 1. The only tangent values that are tricky are these two here. What you'd have to do is multiply by a funny looking 1 to get rid of the square root in the denominator. You'd have to multiply top and bottom by square root 3. So it would become the negative square root of 3 over square root of 3 squared, which is just 3. And this will be the same but positive. Square root of 3 over 3. There's your table. Make sense? Now, as I go to the practice side, we could cheat and look at the table and come up with all of our answers. It'd be very easy to do so. I'm not going to do it that way, though. I'm going to walk you through the process. For inverse tangent, if you're using the hand trick, what you have to do is you first turn it into a fraction. So if it just says inverse tangent of 1, you'd say that's the same thing as inverse tangent, and I'll put in parentheses, of 1 over 1. See how I made it a fraction? Then you turn those into square roots. What is 1 squared? So it's the square root of 1 over the square root of 1. Now here's the problem. This is only saying 2 fingers. By the way, tangent's never, on the inverse is never undefined. So you don't undefine tangent. So it looks like you only have 2 fingers. Well, we got more than 2 fingers. So what do? You write it equivalent. This is saying you had the same amount of y's and the same amount of x's. If you're going to have the same amount of y's and the same amount of x's on the hand trick, it's because you're using 2 y's and 2 x's. So this actually becomes the square root of 2 divided by the square root of 2. That's actually what it is. Therefore, what is the inverse tangent of 1 going to become? Inverse tangent of 1, which is square root of 2 over square root of 2, is going to give us an answer of pi over 4. Pi over 4 is our answer. That up above is how you do it by hand trick. Now, how you do it by graphing is you need to recall that sine is y, cos is x, tangent is y over x. I don't need to write x equals cosine. I don't need to write y equals sine. That if tangent is y over x, I need to remember that tangent is the slope. Whoops. Tangent is the slope. This means I have a slope of 1. Slope of 1 means I go up 1 over 1, up 1 over 1. It's a perfect diagonal line. Tangent is slope. It would look like this. You would take a line through the origin this way, That is a tangent of 1. That's a slope of 1. I'm going to write this equation as y equals 1 times x. That's my slope. Now, right now, how many answers does it look like I have? 2. With tangent, you restrict the negative x's. You restrict the left side. Tangent gets restricted just like sine. Cosine is the one that has a weird restriction. Now, how many answers do I have? 1. This answer's here. It's right in the middle. The amount of pi's that's right in the middle of 0 and pi over 2 is pi over 4. That's why the answer is pi over 4. Okay, part B. Again, the process, you need to first turn this into a fraction. Sine and cosine are always divided by 2, not so with tangent. So you put it over 1. After putting it over 1, you make sure both the values are square roots. The denominator is not a square root, so I'm going to make it a square root. So what's 1 squared? 1, so I make negative square root of 3 over square root of 1. Now I make sure that I'm reduced to where I would have 4 fingers. Would I have 4 fingers here? Is that 4 fingers? 3 y's, 1 x? Yeah, now I can use the back of my hand. I need 3 y's, 1 x. So which finger do I bend for 3 y's and 1 x? Pointer. To evaluate, you flip your hand over. What is that on the pi side? Pi over 3. Tangent works like sine. If your input's negative, your output will also be negative. Sine and tangent follow the same rules. Same restrictions, same rules. If your input's negative, your output's negative. That's going to be my answer here. It's going to be negative pi over 3. Visually, again, tangent is slope. So I would not need to write y equals sine or cos equals the x. I would not need to write that. I would need to write that I have a negative slope. A negative slope, I think that's like approximately negative 1.73. It would look something like that. Let me try that again. I think it would look something like that. That's a slope of negative square root 3 times x. It looks like 2 answers. Why will it not be 2 answers? You restrict this left side. And so if that gets restricted, I now only have 1 answer. This is a negative angle because it goes down. That's why we say it's negative pi over 3. Again, analytical answer, graphical answer. It's the same value. Okay, tangent of 0. If we cheated, what is the tangent of 0 going to be? Inverse tangent of 0 going to be? 0. The answer should be 0. Let's see why. You first have to turn it to a fraction. So this would be inverse tangent. I'm going to put it 0 over 1. You would square both numbers. What's 0 squared? What's 1 squared? Okay, here's the problem right now that says I have 1 finger. We don't have 1 finger. Tangent's always defined, inverse tangent. Inverse tangent is never undefined. So what you do is you multiply it to get a total of 4 fingers. So multiplying by 0 doesn't change that, but I can multiply the denominator by 4, and now I have 4 fingers. Does that make sense? Inverse tangent. We're looking at the back of the hand. I need 4 x's, no y's. Which finger do you bend? For 4 x's, no y's. Pinky, bend your pinky, flip your hand over. What does pinky represent? 0. There's 4. The answer is 0. There's your analytical approach. Yeah. Yeah. Yeah.
I think 0.
I had to have 4 fingers. With sine and cosine, if you don't have the right amount of fingers, it's undefined. But like we had a square root of 36 earlier today. We didn't have 36 fingers. We had a square root of 16 today. We didn't have 16 fingers. On tangent, it's always defined. So you just multiply it out till you get to the right amount of fingers.
Which one?
Well, I multiply both. When you multiply by 0, what do you always get? 0. So it was only the denominator is going to change. On this one, you see how it was square root 1 over square root 1? I multiplied both by 2, and that got me 4 fingers. Yeah, exactly right. Here we go again. X and Y axis on my unit circle. Tangent 0, that means it has a slope of 0. A slope of 0 is a perfectly flat line like that. That's a slope of 0 to the origin. There it is on the x-axis. This is the y-axis. Okay, how many solutions does it look like right now? 2. Why is it not going to be 2, though? You restrict this side. Okay, now how many solutions do we have? Okay, how many radians is it to there? 0. That's why the answer is 0. All right, last one for tangent. This one's on the chart. Negative square root of 3 over 3. Where is it? There it is. Negative square root of 3 over 3. What's going to be our answer for inverse tangent? Negative pi over 6. Notice the input's going to produce a negative input. It's going to produce a negative output. Let's see how we get there. I have a fraction. That's perfect. I need to change this. I need to change this to where they're both square roots. What is 3 squared? So I'm going to change this first to the square root of 9. Now, on 2 of the problems today, we didn't have the right amount of fingers and we multiplied. Do I have 12 fingers? No. So you can multiply. You can also, what's the opposite of multiplying? Divide. This case, since I have too many fingers here, I can divide. 3 goes into 9 how many times? So this is the same thing as inverse tangent of negative 3 goes into 3 once, and 3 goes into 9 3 times. How many fingers is that? 4. That's our location. So back of your hand, you need 1y, 3 x's. What have you been for 1y and 3 x's? Ring. Bing a ring, flip it over. What is ring in terms of pi? Pi over 6. Tangent works like sine, that if you have a negative input, you will have a negative output. The answer will be negative pi over 6. To show you that visually. Once again, tangent is slope. We have a negative slope this time. Tangent is not x, tangent is not y, so I don't need to label that. But tangent is the slope. I have a negative slope. And so my slope would go downward like that. That's y equals the negative square root of 3 over 3 times x line. That's the slope of negative square root of 3 over 3. Right now, how many answers does it look like I should have? Looks like 2 solutions, but tangent, like sine, restricts the left side. You restrict that. And so how many solutions I actually have? 1. And because the angle is going down, it's negative. It would be negative pi over 6. So with all that, let's go practice a tangent problem. We're going to go try DOL number 3. All right. At this stage, finally, we're going to walk through the algebra to start solving some trig functions. So on each of these, we're going to find the value of theta to 3 decimal places. Let's just start here. The algebra. If you were having to solve this, what is your only variable on part A? What's the only thing that we don't know? Theta. To solve for theta, we would do opposites. So earlier in the school year, we've had times where I'm solving for something and maybe it says x plus 7. I say, what's the opposite of plus 7? And you would say minus 7. Or if it said 5x, what's the opposite of 5x? Or what would you do? What's the opposite of what's the 5 doing? Multiplying. What would be the opposite of multiplying by 5? Dividing by 5. Here's my question. If I'm solving for theta, right now it's being signed. I know it sounds weird to say that. It's being signed. What's the opposite of sine? Sine inverse is the correct answer. The opposite of sine is sine inverse. So how we solve this is we take a sine inverse of both sides of the equation. So what happens with the opposites over here, the sine inverse of sine? What happens with those? They cancel. And so we now know that the sine inverse of 1/4 will equal theta. Does that make sense? Whoops, I put a 0. Theta. Cool on that? So what we're going to do here, it just says use a calculator to find those values. Let's go to our calculator. Let's type in sine inverse of 1/4. Open up your calculator. Add a calculator. I want you to choose the trig button. It says trig with an arrow. Find sine inverse. Type in 1/4. We're going to round to 3 decimals, or rather, we don't even have to round. We can truncate. The 3 decimals, AP Classroom, is what it requires. Our answer would be 0.252 or 0.253. Either one would be acceptable. I'm going to put 0.252. Are you okay with that? 0.252. And that's my solution to this problem. Not bad, right? That wasn't hard solving. We did all the setup just to get to this point. Okay, how about this? -3/5 equals cosine theta. What do we have to solve for? Theta. If I want to solve for theta, it's being cosine. What's the opposite of cosining something? Inverse cosine. So we're going to inverse cosine both sides. What happens with the inverse cosine of a cosine? They cancel. And so whatever cosine inverse of -3/5 is, that will equal theta. All right, so I'm going to go over here to my calculator. Again, press the trig button. Cosine inverse of -3/5. And I get 2.214. Good? 2.214 is our answer here. Again, I'm going to do this squiggly because it's approximately 2.214. Notice cosine's different. That a negative input will not produce a negative output. Cosine's the only one that's that way. Cosine, all inverse, all outputs are positive, are 0 or positive. They're never negative. Okay, how about inverse tangent equals -4.5? How do I solve for theta? I said that wrong. Tangent of theta equals -4.5. How would I solve for this theta? We would take the inverse tangent. The inverse tangents cancel out with one another. So we're looking at theta equals the inverse tangent of -4.5. Now, tangent and sine are the same, that if you have a negative input, you will always have a negative output. Let's see what we get here. Trig, inverse tangent, -4.5. You hit enter. You need 3 decimal places. I'm taking -3.52. -3.52. All okay with that? Negative, what was it again? -1.352? Okay, I printed it. I should have slid those over. There we go. Cool? Okay, let's finish this problem up with part 2 here. Part 2 says find all the values of theta such that x equals sine theta, x equals cosine theta, or x equals tangent theta from 0 to 2 pi. So here's what that means. What I'm going to do here is I'm going to separate this problem. Where's my separator? There it is. I'm going to separate this problem, and so this was step 1. We found the calculator to find the answer to 2 decimal places. Now, on step 2, we want to find all values of theta on the interval 0 to 2 pi. So here's what that means. If you were thinking of a unit circle, okay, and I probably should just add in another, oh, well, I'll just leave it like this. Okay, and here's my y-axis. Here's my x-axis. we're dealing with sines, so I'm really caring about the y-axis values. Y equals sine theta, and this being my x-axis. I want to know all the places where the sine has a y value of 1/4. So once again, the sine is y, so I'm going to go in here, and if this is a value of 1, I'm going to say this is approximately 1/4 right there. So I'll add that in, y equals 1/4. Y equals 1/4. Remember, this is a maximum value of 1 there. This would be a minimum value of -1, and this would be 0. Okay, with that, there's two solutions. This problem, though, is not restricted. There's no restriction because it does not say sine inverse. So how many answers would we have? This says between 0 and 2 pi. Actually, there is a restriction. The restriction is from 0 to 2 pi. How many solutions will we have? Well, the answer is 2 solutions. We would have an answer. We would have an answer anytime we have an intersection, which means we have 2 intersections. We have an intersection here and an intersection there. Those are my 2 values. So what are these values? Well, notice it's the same length. This is the theta right there that we solve for. This angle right there, though, would be a little bit more. This one actually would be this same distance taken away from pi. So if this is theta, this other angle is going to be pi minus theta. Those are going to be my 2 solutions. So find all values of theta. So we already have one answer. It's right here. The theta equals 0. Well, is approximately 0.252. The other value would be theta equals pi. Let's call it theta 1 here. Theta 2 would be that pi minus theta 1. Because it's not quite all the way to pi. It's the same angle amount subtracted from pi, going backwards from pi. So if I go back to my calculator here, if I go back, I'm going to take this first value right there, and I'm going to take it away from pi. So pi minus that amount. That's actually going to be my next answer. So approximately 2.888. Again, you could round that if you wanted to. I need to have a approximately 2.888. That would be my second solution there. Those are my 2 values, my 2 different theta between 0 and 2 pi, where to have intersections. Okay, now that I've shifted everything over, let's now look at part B. So now I want to know where the cosine is equal to -3/5. Well, visually, here's what that means. If you draw your unit circle, cosine is x. So this time I want to pay attention to the x-axis. So cosine is x. So this time I'm going to say x equals cosine theta. Don't have much space for that. Let me try it one more time. X equals cos theta. And here's my y-axis. I'm looking for answers between 0 and 2 pi once again. We know cosine has to be -3/5. Well, -3/5, this is, as a reminder, that's the value of -1. This right here is 0. This value is 1. We want to know -3/5. That's somewhere in between here. Let's just approximately put it right there. I'm going to draw, that's when x equals -3/5 right there. X equals -3/5. Now notice we have 2 answers. Because this is not restricted, we actually have 2 separate answers. We have the answer right there, which we already found the first time. This was our first theta that we found. That was our first theta. I'll call it theta 1. Okay, that was our first theta. Now I have a second answer. The second answer is when it cuts through this point, which we'll call theta 2. Now, mathematically, this one's easy to find. Theta 2 is just going to equal the negative of theta 1. I don't know if that makes sense to you, but this angle, theta 2, is just the opposite of theta 1. So if this is theta 1, let me put theta 1 there, and theta 1, then that will just be the opposite of it. Okay, so that's the idea. So if this is theta 1 is 2.214, and again, this should be approximately. Then theta 2 here would be approximately negative 2.214. That would be my answer for part B, or part 2, I should say. Again, if this is part 1, this is part 2. If this was part 1, this over here is part 2. All right, and now let's look at C. Tangent. What's going to happen with tangent? It always works the same way with tangent because tangent is slope. So here's my x-axis or my y-axis. Now there's my x-axis. So if I label these x, y, tangent is slope. We had a slope of negative 4.5. That's really steep negative slope. It's going to be a really, really steep negative slope, something like that. That is where we have a slope of negative 4.5, like that. So we have two different answers. The calculator gave us this answer here. We'll call that theta 1. Okay, this is part 1. So now I'm doing part 2. Theta 1 is this value right there. Well, to get the other value, this theta 2, it's going to be, since they are straight across the circle, if you think about straight across here, it goes from 0 to pi. They're a pi amount. A straight line in radians is pi away from each other. So theta 2, it's going to be theta 1 plus pi. Or you could always just say pi plus theta 1. That's how tangent always works. The second answer, you always will just add a pi. So if I go back to my calculator, the second answer will be, I take the same value here, but I'm just going to put pi plus that, because pi will make a straight line. And so this value right there will be my second answer, approximately 1.789. Approximately 1.789. So theta 1 is negative 1.352. Then theta 2 is approximately 1.789. And that would be part 2's answer. All right, as we pick on up, some properties with inverse trig functions. As I was telling you, a sine and a sine inverse, these are opposites of one another. Here's what's a little tricky though. They are opposites one another when if you're dealing with sine inverse, your inputs have to be, remember sine inverse, the y values have to be between negative 1 and 1. If they are in between 1 and 1, it'll be a straight up cancel, and the input will become the output when you take a sine inverse of the sine. Or the same is true for a cosine of a cosine. Now tangent's different because inverse tangent has an input of all reals. So you could put in all reals and then you'll get a value that's somewhere between negative pi over 2 and pi over 2. And once you place that back in the tangent, the output is all reals once again. But when we deal with values where it's the sine inverse of sine, for these to be able to cancel properly, the values have to be between negative pi over 2 and pi over 2. Remember, sine itself is not restricted. So for these just to cancel perfectly, my value has to be between these two values. If it's not, whatever is x will not end up being x. It'll change. What do I mean? Let's just say you were looking at sine of 3 pi over 2. Let me give you an illustration real quick. If we were looking for sine of 3 pi over 2, so sine of 3 pi over 2, 3 pi over 2 is outside of sine's restricted. All right, let's do sine of pi. That's an easier one. If I'm looking for sine of pi, well, sine of pi it's the y value right here, which we know the value is 0. That's negative 1 comma 0. But when it comes to the restriction, when you come to that stage, you would restrict this value out of there and you would not get the answer of pi. Even though I initially give you a pi here, put a pi, the final answer would not be a pi because what happens, sine inverse or sine of pi, it generates a 0. You would then find the sine inverse of 0. And on a restriction, sine would not look on this left side. It would look over here and it would say, where's the y value 0? It's right there. That's where the y value is 0 on the restricted. And so the answer would be the radian of 0. And so this sine inverse of sine of pi would actually generate an answer of 0. So all this is saying is what it does not mean is the values will be undefined. What it means is the answers will be different. Okay, so I want to walk you through some of that. So I'll write that down one more time. Sine inverse, you could type that in the calculator and see for yourself, of sine of pi is actually going to equal 0 because this is going to get restricted out. So it's going to look for the y value of 0 on this side of the graph, which happens at 0 itself. Okay, that's why that happened. So let's look at some of these. All right, we're going to look for the sine inverse of sine of 2 pi over 3. So I'm going to draw a unit circle here. And sine 2 pi over 3 is just past pi over 2. So if I labeled this, here's 0 and 2 pi. Here's 1 whole pi. Here is pi over 2. Well, 2 pi over 3 is approximately, let's just place it right here. Let's say that's 2 pi over 3. Okay, so going around the outside of the circle, counting radiuses, you would have 2 pi over 3 radiuses to get you there. Now, if you're looking for sine of 2 pi over 3, what that means is I want to know what is that y value. That's what sine is looking for. It's saying, what is the y value right there? That's what it's saying. Sine of 2 pi over 3 is wanting to know, what is that y value? Well, we could do hand trick, and if you did hand trick, you would start with the pi side, 2 pi over 3, that's your pointer finger. You'd bend your pointer finger over, you'd flip your hand, you'd say, okay, I have square root of 3 over 2 there. That's what that value is. It's the square root of 3 over 2. So this right here could be substituted to be with the square root of 3 over 2. So I'll go ahead and write that out. This all becomes sine inverse. And when you substitute sine of 2 pi over 3, you substitute in the square root of 3 over 2. And so now I'm applying the inverse. Well, when you apply the inverse, half the graph gets canceled. I should have put that this was y equals sine there. This is x. So now when I'm doing a sine inverse, I have to restrict. Now sine is y, so I don't restrict the y's, I restrict the negative x's. This part gets eliminated, it gets restricted. Now, when I restrict this side, that means my answer has to be this solution right there. So my solution is actually going to change. These do not just cancel straight up and leave me with 2 pi as an answer. What I'm going to find out is my actual answer is going to be this intersection. Now, what will generate square root of 3 over 2? Again, you can use hand trick, 3y's, flip your hand, but it'll just be the pi over 3 in this quadrant, which the pi over 3 in this quadrant is 1 pi over 3. And so that would be the answer to this problem. Pi over 3. We can check that in the calculator here in a moment. You know what? Change of plans. I'm going to go ahead and just show you right now. If I did the trig inverse of sine, or if I went to the trig button and then did sine inverse, and it was 2 pi over 3, 2 pi over 3. You press enter, you get this answer, which is not 2 pi over 3. That is actually the same as pi divided by 3. So you can see that these do not just cancel out and remain 2 pi over 3 because of the domain restriction. You have to make this equivalent within the right domain. Okay, so to go quicker, 3 pi over 4. The question you need to think through for cosine inverse, will 3 pi over, actually this is not going to work because inverse, that should be a square root. That's going to be undefined. I can tell you right now, this is going to be undefined. Some of you are like, whoa, why is that undefined? because cosine inverse has a minimum of -1 and a maximum of +1. That is the radian, which should be the output, not the input. So this one's going to be undefined. Negative 3 pi over 4 is like 3 times 3.14, 9 something divided by 4. It's going to be 2 point something as a decimal. And so if I type this in the calculator, it'll say undefined. It was cosine of cosine inverse. Let me just use this button. And it was 3 pi divided by 4. 3 pi's divided by 4. You'll notice it's going to say undefined. Error, non-real calculation, does not work. And visually, here's the picture to prove it to you. Cosine is x, so we're paying attention to the x-axis. I'm going to make a longer x-axis. Cosine is x. I'm first looking for the cosine inverse of 3 pi over 4. Well, 3 pi over 4 as a decimal is 3 pi's divided by 4. This is what I was saying is going to be 2 something. 2.356. And so if this is an x value of 1, actually I'll go label from here, -1, 0, 1, let's say that's 2. Then 2.34 is somewhere just after it. That is x equals 3 pi over 4. Notice no solution, no intersection. That's why that does not work here. Okay, this time, again, we're working with inverse functions. This is proper tangent of 5 pi over 6. So what I want you to think through is on the unit circle, if 5 pi over 6 would be in the inverse tangents domain. Okay, so sine is y, cos is x, tangent is y over x. Since it's y over x, you restrict the negative x's. So tangent 5 pi over 6. First, that's slope. 5 pi over 6 is like the ring finger coming from here, so it's a slope. Tangent of 5 pi over 6 would be a slope that goes through from here. That right there. That's 5 pi over 6 this way. We're saying that's 5 pi over 6. I'm putting that on. The tangent would find its slope. 5 pi over 6, I'm bending my ring finger, I'm flipping my hand, I would have a negative x, so I'd have negative square root 3 over 2, and then my y would be positive square root 1 over 2. Okay, so when you're finding your tangent, this initial part would be the y over x. So we'd say this is the same thing as tangent inverse, and I'll substitute. Tangent of 5 pi over 6 would be the y, square root 1 over the x, negative square root 3. You can ignore the 2's because those simplify out, they cancel each other. And so now I'm doing this inverse. So again, tangent is slope. You would look at this line because that's the same slope. That's a square root of 1 divided by negative square root of 3 slope right there. But when you do the tangent inverse, you now restrict. This gets restricted. And so this becomes the answer. And so if this was 5 pi over 6, it's a pi over 6 answer. Since we're going down from 0, this would be negative pi over 6. That's going to be our answer this time, is negative pi over 6. That'll be our solution. And so notice it's always the same family of pi's, the answer. The answer will be always the same family of pi's. Tangent inverse of tangent 5. Oops, I forgot the pi. 5 pi over 6. Enter, I get this. And I'm telling you that's negative. Oops, I hit the wrong button. Negative pi over 6. Notice they match up perfectly, same decimal. All right, and one more time. Cosine inverse of negative square root 2 over 2. This is going to work great. Negative square root of 2 over 2, we're talking about cosine, so we're dealing with the x-axis. So we're paying attention to the x values here. So if I look at the x-axis, x is equal to cosine. We want the cosine value, again, this is a value of 0, this is a value of 1, this is a value of -1. Negative square root of 2 over 2 is something like negative 0.7, I believe. So I'm going to come over here and just put it, I don't know, about right in here. And I'm just going to suggest that that is negative square root 2 over 2. Okay, so when you're dealing with cosine inverse, you restrict out the negative y. So I'm restricting on the front end. I would not use that value down there. So this gets restricted. So what I would get on the inside is I would look for the radian measure that goes from here to here, which if I'm using the inverse hand trick, I count 2 x's from the bottom, then my middle finger, I flip over my middle finger, and I realize it has to be a pi over 4. Since it's in the second quadrant, that is 3 pi over 4. So that's evaluated the inside. I get cosine of 3 pi over 4. Now, when you go to evaluate cosine of 3 pi over 4, now I'm saying, okay, what is the x value at 3 pi over 4? Well, it's sitting right there. That is the x value. This one reverts right back to the negative square root 2 over 2. So what's the point of going through all this? If you have an inverse on the inside and it's defined, you can just cancel. If it's not the inverse on the inside, the restriction later might change your answer. So if the inside is a normal function, you might have a answer that's changed slightly. If you have an inverse on the inside that is defined, then your answer will remain. It never changes. All right. With that, you can go try DOL number 4. All right, take a look at example 6 now. It says to evaluate the following. So now we're going to break this down and see what happens when you're taking the cosine of a sine inverse and things like that when you're changing up your trig functions. So let's start with the sine inverse of -1/2. I'm going to start there. So sine is y. This time, since I'm finding sine and dealing with cosine, I'm going to write both the y-axis is sine and that my x-axis is cosine. Now, the sine inverse, that's telling me my y value needs to be -1/2. So just a reminder for the y's on a unit circle, that's +1. This is -1. Actually, let me write this on the left so it doesn't look like a -1 up there. And there we go. That's 1. And this would be 0. I need to have a y value of -1/2 right in there. -1/2. That's the y value I'm coming through with right there. That's a y value of -1/2. Now notice at this stage I should have 2 solutions. We would think we'd have a solution on the left and on the right. Now if I'm dealing with sine inverse though, I need to include all y's, but I can restrict the negative x's. So from the get-go, I'm actually going to restrict this side of the graph. I cannot have an answer on this left side of the graph because it is restricted out of there. My only potential answers are going to come from any value between -pi over 2 and and positive pi over 2. My answers have to be somewhere in between there. So it's going to be this point. To go ahead and find the sine inverse here of that point through there. Using the back side of my hand to have one y would be I bend my ring finger. If I flip my hand over, the ring finger is pi over 6. This is -pi over 6. Remember with sine, if you have a negative input, you're going to have a negative output. So I'm now looking for the cosine of -pi over 6. -pi over 6. So now I look for the cosine there. I know the y value. The question is, what's the x value? So that point, we know the y value is -1/2. The question is, what is the x value? So at pi over 6, again, pin that finger, flip it back over. I'm getting an x of square root 3 over 2. And I know it's positive because it's to the right. Since that's my point, my answer is going to be the square root of 3 over 2. That will be my answer for this problem because that's the cosine. I'll check it in the calculator. I'll prove it to you right here. We're looking for the cosine of sine inverse -1/2. -1/2. We get this value, and I'm telling you that is the square root of 3 divided by 2. Notice they're exactly the same. So we got that one right. All right, part B. Part B, let's now look at sine of cosine inverse of 5/13. Well, I draw a unit circle here. Cosine is x. Again, since I'm dealing with sine and cosine, I'm going to label both axes. So x is cosine, y is sine. I need 5/13. If I label these axes, this is -1. I'm doing x first because cosine's on the inside. So I'm labeling between there. 5/13, that's less than a half. That's somewhere in here, 5/13. I could have two potential answers, you would think, to have 5/13. Let me actually add that as a line. Let's go 5/13. Let's say it's right here roughly. That's almost halfway. We'll say that is x equals 5/13. It looks like I have two answers. But when I'm dealing with the inverse of cosine, since I need all x's, what I don't need are negative y's. I don't need the negative y's. So what I would do first is I would actually restrict this graph on the lower half. The inverse of cosine is x. I don't need the negative y's therefore. So I would restrict that, which means this is my only potential answer right there. So now what I would do is taking an angle through there. This inside would produce some theta that goes to that point. It would produce some theta that goes from there to there. I'm just going to call it theta for now. Okay? So this is equal to sine of whatever this theta is. Now, I don't know what that theta is, but I don't need to know. Because when I want to find the sine of the theta, what I'm looking for is what is the y value there. And so ultimately what happens, since I know the x, that point right here, we know it has an x of 5/13. What we need to know is what is its y value. And the way to do that when you're dealing with these values is you change this to a triangle. And as a triangle, when I change it to a triangle, let me, 1, 2, 3. When I take that as a triangle, I want to take those 3 spots. Oh, it's not copying all of them. Well, darn. Okay, I'll just go one at a time. When I take this as a triangle, what I'm going to do is I'm going to say the x value is 5. We're going to say the x value is 5. We're going to say the r is 13. And the y is the unknown. And we would do a Pythagorean theorem to solve that. So I'm going to say that x squared plus y squared equals r squared. We plug in 5 squared. We don't know our y. We know our r is 13 squared. Or r is 13, so we square that. 5 squared is 25. So it's 25 squared plus y squared equals 13 squared is 169. When you subtract your 25 from both sides, you find out that y squared is going to equal 144. The opposite of a square is a square root. And just like that, we now know that y equals 12. And it's got to be a positive 12 because it's going up. Now that I know it's 12, when I translate it back to this circle, since that was 5/13, we're going to say that the y coordinate is 12/13. And that's going to be our answer, 12/13. Okay, when I type this in the calculator, you'll see that it will agree with us. The sine of cosine inverse of 5/13 is this, and I'm telling you that is 12/13. Uh, control enter is what I'm looking for. Control enter. Notice same exact decimal. All right, and if I want to try part C now, it says if 0 is less than x, which is less than or equal to 1, evaluate sine, cosine, inverse of x as an algebraic expression in terms of x. Okay, so here we go. Let's figure out what this is talking about. Unit circle time. We're going to have sine and cosine, so I'll label both my axes. We know that x is cosine, y is sine. This is saying our x value is somewhere between 0, greater than 0. So if you think of x values, here's -1, here's 0, here's 1. We know it's somewhere between greater than 0 but less than 1, which means this part is restricted. And we actually know that it's not even going to be equal to pi over 2 or negative pi over 2. We know that because it's not going to equal 0. It's going to be in between. So it's going to be any value from here to here with open circles on the end, if that makes sense. Okay, so as I go around, it's going to be any of those values from inside there. This is an x value of 1 right there. Okay, so it's going to be some amount of pi's in there originally. All right, it says cosine inverse of x. So we start there. So this is restriction on, you know what? I'm looking at the input here. I'm messing up. This original x is somewhere between 0 and 1, but it's cosine inverse. I restricted negative x's. I need to restrict negative y. So let me, hang on. I'm sorry. I just need to start this one over here. I'm going too fast. Not paying attention. Okay, cosine inverse. That means cos is x. We need to restrict the negative y's. This part of the graph gets restricted. So we're looking at values between here. Now x has to be positive. So now let me do that. So if this is an x value of -1, 0, 1. Oh, I'm still looking at the wrong thing. That's the input. Yeah, the input is a positive number, which means this x value, we're somewhere between here. We cannot be equal to 0. So that means I cannot be there, but I have some x value that's over here. Okay, so I have some x value in between greater than 0 but less than or equal to 1 for this. So I'm just going to choose any random point. It doesn't matter what I'm going to do because we can't find anything. It just says x. So let's just say we have an x value right there. So that would qualify. We're just going to say that that's it. That right there would represent the theta. So this will produce some type of theta. That's the theta right there. Now what I would need to do is find the sine. Well, sine is y over r. So I would need to know what's the y value at that point and then divide it by the radius. Well, the radius we can solve for right now. We know the radius is 1. So to find the y, that's the whole trick. The y value here, whatever the y is, that's going to be my answer. Here's what I know. This is just, they called it x in our problem. We don't know exactly how long it is, but basically I'm working with this triangle that goes here, here, and there. I'm working with that triangle. So let me bring out my pieces. And all we know at this stage is that this is x, and this is a value of 1. We don't know the y. That's what I'm looking for. I'm looking for this y value so I can find the sine. Okay, so to do that, I would use Pythagorean theorem. X squared plus y squared equals 1 squared. I'm solving for the y. So the first thing I would do is I would subtract x squared from both sides. And so the y squared would be equal to 1 minus x squared. And then to get y by itself, I would take the square root of y. And so y would equal the square root of 1 minus x squared, whatever that is. These do not cancel because the 1 in front can't cancel the square. So that's the y value. Since that's all I know about the y value, this point right there would have the coordinates x, whatever x is, and the y would be the square root of 1 minus x squared. That's a really weird way of saying it, but that's what it is. Sine is interested in the y value. Therefore, that is the answer right there. The sine, which is the y, of the cosine inverse of x would equal the square root of 1 minus x squared. That is my answer. Now, very, very weird problem, just to leave it like that. So to try to make sense of it, what I'm going to do is I'm going to plug in a couple values, and I'll prove to you that this is always true. That if I wanted to find the sine of the cosine inverse of some value between 0 and 1, what I'm going to do is I'm going to plug in numbers. And I'm going to pick a number between 0 and 1. I'll do 0.1 first. And I'll press enter. That value, what that must be, is the square root of 1 minus this number right there, squared. Notice it's exactly the same. Okay, let's do another one just to test. I want to pick another number between 0 and 1. A number between 0 and 1 would be 0.5. If I tried that, then what that would mean is this answer, it would be the square root of 1 minus this same input. Notice, same answer. I could do it one more time. If I'm picking a number between 0 and 1, let's say I chose 0.75, then that means my answer would be the square root of 1 minus 0.75 squared. Notice that they always match up. All these values are exactly the same. So we did it correctly. All right, so I added that in. That's a proof of what we just said there. All right, now go try deal wheel number 5 on the back of the packet. All right, last example here, example 7. An airplane flies at an altitude of 5 miles towards a point directly above a house. There's the altitude, that means the height above the ground, 5 miles. First off, what I'm going to do here is I'm going to write this as a y value because I see this as a triangle. This is labeled as x. This would be my radius or your hypotenuse, if you wanted to call it radius or hypotenuse, whatever. It says first, write theta as a function of x. So I got to include the x, and I'm given the y value. So what does that mean? If I'm going to write it as x, you could write it like the functions that include x, cosine, it would be true to say that the cosine of a theta is your x over r. That would be true, but that couldn't solve anything. What I would use this one is x over y. So x over y, if you did not know, is cotangent. Cotangent by ratio is x divided by y. So if I wanted to solve this, it says write theta as a function of x, what I would do is I would actually take this ratio and say that the cotangent of this theta will be the x value divided by my y, which is 5 miles. Okay? That's how I would solve this. Now, it says find theta if your x equals 8 miles. So if x here, if x is equal to 8 miles, now I can find theta because I could say that the cotangent of theta is 8 divided by 5. Let me make sure this is clear to everybody that this is my trig function. And to solve a cotangent, you'd have to perform the inverse. What's the inverse of a cotangent? Well, now you know it's a inverse cotangent. So what I would do is I would take an inverse cotangent of both sides of this equation. These two would cancel each other out. And so theta is going to be equal to the inverse cotangent of 8/5. And I'm going to find out what this is as an angle. So I'm going to go to my calculator. And here I'm going to do it as both a radian and a degree. So calculator, the inverse of cotangent of 8 divided by 5. This is in terms of radiuses, how many radiuses it would take. But this problem is actually a degree because it's a triangle. So I'm going to change it to degree. And I'm going to copy and paste this. And that's how many degrees it is rounded to 3 decimal places. Now I'm going to switch back to radians so I don't forget. But this would be my value there. Let me go ahead and paste this in. And so our theta is approximately 32.005 degrees. And that's going to be my answer for part B. And I'm going to make clear on this rate that this right here is the radians. That would be the number of radiuses if you're looking at a circle. This right here is in degrees. Okay, and so on this theta, if you were counting degrees from a protractor, that should be, if it was drawn to scale, approximately 32 degrees. And if you were counting, if you had a circle here, if you had a circle, and you were counting the number of radiuses, so here's your radius right there. If you're counting the number of radiuses from there to there, that right there would be, if your theta is 0.558 radiuses or radians. That's the idea of this. Now that's really messy, so I'm going to take that off because that's just, yeah, it's just really messy to leave on the problem, but that's how it works. Now with that, go ahead and try DOL number 6. All right, finally, we've come to the end of lesson 3.9. Go ahead and scan this QR code, upload your answers online, submit them in.